Welcome to the another session in Frontiers in CFD. So today's analysis on CFD simulation for heat transfer enhancement in pulsating heat pipe with fins. So today's objective is to generate the 3D geometry of pulsating heat pipe with fins, to generate the mesh on computational domain and apply the name selection so as to apply the boundary condition in the setup part, to define the material model selection and running the iteration with suitable time step size. So this is likely to take more time, as I said. So for the pulsating heat pipe, the number of iterations we have to take it more. So that definitely the time requirement will be comparatively on the higher side for these cases. So welcome you all to another session on Frontiers in CFD. Today we will see the CFD simulation for pulsating heat pipe with fins. So first phase will be to prepare the geometry, and then we'll slightly move towards the meshing and then applying the boundary conditions, and then finally we'll run the simulation. So let's start with the workbench window. So click on fluid flow fluent, go to the geometry, click on new design modeler geometry. So first phase will be to set the units. Once we are setting the units, so I will set it to millimeter. Then click on any one of the plane. You will see this is blue, this is green, and this is yours. Red, green, and blue. You will see X, Y, and Z. So first of all, set the unit, that is we are set to millimeter. So create, I will say primitive, a kind of box arrangement here. So instead of add material, I will make it add to frozen. So here first of all, X component I will take it, origin definition I will take it 0, point 1 definition I will take it 0, Y also will take it 0, then Z also I will take it 0. X component now will change, so we'll take it 27 here. The Y component will take it 115, and Z component will take it to 10 mm. So likewise we have proceeded. So let's click on generate. So this is the box type of arrangement which has been generated. So our aim is to prepare the heat pipes, then we'll try to provide the fins as well, and that's why we are providing with such kind of combination. So next step is, as I said earlier, so first we have prepared the X component, that is 27, Y component 115, Z component will be equal to 10. So this is the box arrangement which we have prepared. Now let's create one more plane. So here I will just create a plane. Now this plane, I will take the base plane as XY. So here the base plane I will take it XY. First of all, I will click on offset Y. So here, so I will just set offset Y. I will put some value, let us say 12.5. You will see it has been shifted up. Okay, so it has been shifted here. So this is offset transform value 1. Then I will just select offset X. So here I will put some value that is equal to 4.5 mm. Then one more offset I required, so I just select offset Z. So this value I also select, that is equal to 5 mm. So likewise we have generated a kind of arrangement. So this will be now somewhere at the center of this particular box. Center means, so along the Z we are trying to make this plane to be available as a origin from the center. So likewise we are making the arrangement. So now let's click on generate. So this is the plane which is generated. So from this side you can see it is exactly on the center between the two ends. So this is what the first phase we have done. Now what we will do, we will generate a kind of we can say, you can draw a kind of sketch. So on this particular plane, so let us say this plane, I just create a sketch over here. So go to the sketching option and just try to draw um, the arrangement which will involve the sketch of the path that we have to follow. So let us say this is one vertical line which I have taken. So let's provide the dimensions to this line. So I will specify these dimensions to be equal to, let us say, 90. So it is somewhere up to this. Now one more line I will draw. So from this center it will go horizontal. So take the dimensions to be equal to somewhere around now. The thing is we want to generate a sketch for this particular arrangement. So for this particular sketch arrangement which we are considering, so I need some center distance between these two. So likewise accordingly we'll proceed. Okay, so the distance between the two will be equal to, so I will just put it here 9. Then similarly I will try to draw a circle. So one thing which we have to carefully remember is the diameter will be of that pipe will be equal to 3 mm. So radius will be equal to 1.5. So the distance between the two will be equal to 18. So I take the distance that is equal to 9. So just try to draw a circle here from this end. The dimensions of this will be equal to 18. Okay, so it will touch both of the end. So draw one more line from this end horizontally. Take the dimensions to be equal to 9 here. So specify this value to be equal to 9. Then draw one more circle of diameter okay, so this is a circle which we have drawn. Now let's draw a line up to this and join this with the bottom end. Now trim out the unnecessary things which are not required for us. So I just go with the trim operation. This is not required, this is not required, this is also not required. So this is also not required, this is also not required. So whichever the things are not required, you have to remove this and keep the remaining things. So simply observe the sketch now. So again the sketch which we have prepared, it will be again from the center one. Okay, so this is one thing that we have to carefully do. There should not be any additional points in the sketch, otherwise there will be errors while generating the geometry. So this is one care you have to take when you do the trim operation. Okay, so we have done the trim operation. So just check one more time if there is some thing is available. Otherwise we can proceed for the next step. Okay, so this is one sketch which we have prepared for the we can say the path which will be followed by the pipe. So I will do one thing. Now I will create a primitive that is cylinder. So instead of add material, I will make it now slice material option, because I will have this particular object along this particular, I want along this particular path. So here the base plane which I will select will be equal to the cylinder. The cylinder base plane I will consider with respect to the previous case, and again it should be from the center of this particular sketch as well. So let's check if I select the plane 4 here, so make it apply. So it will be now here. So now next thing what I will do is, I don't want this to be in Z component, so I will put it in Y component. So let's make it equal to 0. So you can see the orientation now as per the requirement. The radius we need is 1.5. So just change the radius to 1.5. So you can see now here the object is been prepared. So this is the primitive which we have generated. Now we need this primitive to follow this particular path throughout. and that's why we will select this. Okay, so let's make it generate. So if you click on generate, you will see this is a portion which is available here. So this is one solid part, and this is your the cylinder which has been generated. Now you can make this cylinder as a thin here itself by providing certain thickness, or you can do it later on as well. So I will prefer to do it later on once I have completely generated the whole cylindrical object. Now I will do with this operation which is called as sweep. So for this case, what I will do, I will hide this body and then I will do the operations. Okay, so profile will be now, this will be my profile. So make it apply, and I will select this particular path. So let's make it apply. So if you are finding it errors, it means the sketch is not proper or the sketch is not complete. So this is the reason you may find some error, but here we are not observing any kind of. So accordingly we'll try to generate, and accordingly whenever the sweep operation has been generated, it should be generated along this particular object. So let's show all bodies. Now you can see properly the sweep operations has been generated. Sometimes you will see the arbitrary cases, like the sweep is not proper, where the thing is you may not see a proper circular section or proper circular section like this. In that case there may be some error with the sweep operation. One more time, just check it from the sides as well. This is exactly at the center point along this we can say object. So this is the correct thing which we are having right now. Okay, so this is the outer portion which we are having. This is the inner pipe which we have generated. Now we can do one operation which is called as thin. So there are two ways of doing this. So right now we have generated the whole object, and then we'll make this as a thin operation as well. So both so this is one way by which it can be done. Second way, while generating the cylinder itself or while providing the sweep, you may provide a kind of thin surfaces as well. But we are not going to proceed with that option, because first what I will do, I will just hide this object which is on the outer side. So this one, I will just hide the body. So you will see now there are two objects which are been available. One is here and this. So I will first unite this object and then so create, go to the boolean, make it unite and generate. So now this will be a single object which is available. So this is your outer case, outer we can say box, and this is your the object which has been present here. So let's one more time make it show all bodies. So now both the bodies are visible here. Now what I will do, for this particular body, I want again this particular surface to be thin from inside. So this is one operation which I can do. Other operation is that whenever you generated the cylinder, that time itself you can actually provide thin surfaces. Okay, so inner thickness if you provide here itself, so accordingly also that's the task can also be completed. Let us say if I put the value to be equal to 0.25, and let's make it generate. So if I just put this is 0.25, this is first and this is your second. So likewise things can be generated. Okay, so here the sweep operations also need to get updated. So let's make it generate. So here I will just come back and I say it is no. I will just back to the initial stage which we are having. So this is the two objects which we are having right now in sweep operation as well. So if I just go as a thin surface, you may have the option which is available. Okay, so this is the first body which we are having. So let's make it show all bodies. So this is the first and this is your second. So one more time hide this, and now what I will do, I will use the thin operation which is available here. So select this faces and let's make it apply, and I will provide the thickness. So what thickness I will provide here, I will provide a thickness of 0.5 mm. So let's make it generate. So now this will become thin from inside. Okay, so this is the second way by which we can make the internal surface as thin. So this is one way where you might require some rework, as we observed the edges was visible. So this is the second option by which easily we can do. Now this is we have done the thin operation on the internal part, and we have provided thickness that is equal to 0.5 mm. So total will be equal to 1 mm. Now what I will do is I will select all the internal faces of this particular object. Okay, so I just want to select here. So here I select the internal part, so deselect the outer one, select here again internal part, not the outer one, select here again internal part, not the outer one, select here again internal part, not the outer one. So now all the internal faces are selected. So what I will do, I will go to the tools, I will select the fill operation and make it apply. Just carefully observe what changes occur here. So earlier there was 2 part 2 bodies, now it is showing 3 part 3 bodies. So this is your solid which is outer, this is again solid, and this is your now will be your fluid zone. So just observe the definitions here. This is showing solid, this is showing name is showing solid, but I need to change this name as fluid. So let's make it fluid. Okay, so this is your the outer region which is related to fins. So this will be actually relates to your copper pipe. So right now I will not proceed in naming it, because I need to delete most of the parts, and that's why we'll do it at the later stages. Okay, so first phase which we had is we have generated uh, 3 specific zones. One is this outer one, then we have the pipe one, and inside the pipe there will be fluid. So these are the 3 zones which we have generated. Now what I will do, I will create one more plane. Now the base plane for this case I will take it here ZX, not the one which I had taken earlier. So here I will just update. So from this I will just go upside. Now at what distance I will do, I will just offset it by 75. Just carefully observe where it goes here. So it goes at this location. So let's click on generate, and now I will do one operation which is called as slice. So I just generated here the 2 parts. Okay, now what is the purpose here is, the purpose here is to I need fins on this particular outer element which will be coupled with the copper pipe, and that's why this particular things which I am doing. So one more plane which I will generate. Now it is from plane 5 I will generate, make it offset, and let's put it to 15, and let's make it generate. So let's have this one here. Now one more time do the slice operation, and let's make it generate. Okay, so this is how the 3 different regions which you are able to see. Now the whichever regions we don't want, we can actually remove that zones as of now itself, so that there will not be much complications here. So these are the 2 zones which we don't require. So I just go to the create, and I will select body delete, and just go and delete this operation. So we left with only this region, this region, and this region. Now from this I will just go ahead. So from plane 6 I just offset z by equal to 1 mm. So just make it generate, do the slice operation, make it apply, generate. So one more time I will generate one more plane, I will offset it by z 1 mm. Now why I am offsetting it by 1 mm, I want a thickness of the fin to be equal to 1 mm, and that's why I am again slicing the object at 1 mm. So one by one we'll generate all the planes. So make it offset z here as a 1 mm. Let's make it generate, and just do the slice operation. Okay, till the end we are reaching, so we'll do that operation. So one more time, just click on plane, make it offset z, say put it to 1, I make it generate, and then do this slice operation. So let's click one more time, plane, make it offset z. So don't forget to do the slice operation, otherwise things will be slightly get complicated. Okay, so one by one we are doing the same task. So make it offset z, put it 1 mm, and let's make it generate. Next put it one more time, offset z, put it 1 mm, let's make it generate. And okay, so I need to do slice operation, I just forget. So click on plane 12, make it slice. Okay, then one more time do the slice operation now for plane 13, and do the slice operation. Okay, So next, one more time, generate offset z, make it by 1 mm, and let's make it generate. So carefully do the slice operation, don't forget to do it. So one more time, offset, we'll put it z here, 1 mm, just make it generate, and let's click on slice. So carefully you have to do the slice operation for each and every case. So till the we reach to the topmost point, we have to do the same task. So we are up to here. So not necessary, I have provided thickness that is equal to 1 mm. You may have your own different value. This is, just make it slice and make it generate here. So just one more time, here offset z 1 mm, make it generate, and then you have to do the slice operation. So till the time we reach to other end, we'll do the same task of doing the slice. So try to simplify the object, so that there will be less complication left, because there will be too much of rework that may have to be done further, and that's why we have deleted the unnecessary parts which are not required for the geometry. So let's click on slice, make it apply, and generate. So there will be more number of fins, as you can see here. So in between that, we will try to delete the things which is not required for us. So if the problem is of say you are having a fluid which is again flowing through this particular section, in that case you can specify this as a y with the help of fluid, and again you can uh, specify inlet outlet for the fluid as well in the next step. But we are not doing any kind of fluid flow arrangement here, but we'll just have provide a convection coefficient on the fin surfaces, and accordingly we'll try to do the simulation. So let's one by one generate the planes till we reach to the end point. So make it slice operation and generate. So one more time, make it offset z, make it 1 mm, then do the slice operation, make it generate. Okay, so okay, just okay, so there may be some intersecting parts here. If you see, this is the intersecting part here. So what I will do, I will simply put it 1.1 mm, or maybe slightly lower than that. Then there will be a slice operation will be successful, just like you are observing here. Next, one more time. Now I will put it to 1 only. I will not, this was the intersecting part, so that's why it was showing error. So let's make it generate and make it slice. So same thing may happen here, so you have to be careful with that, and then accordingly you may need some kind of variations as well. So let's make it generate and then do the slice operation. So if slice operation is unsuccessful, in that case you can go with that particular option. So one more time, just make it offset z here, let's put it to 1, and make it slice. Okay, so here you can see now, uh, above this the things are not important for us. So we are up to here, the things are not important for us above. So I just go here. This is not really, if you are considering the cases of fluid which is flowing, in that case you can consider, otherwise I can remove this part which is not required for me. So I just select this part, go to the body delete operation and click on make it apply and generate. So you can see this is the part. So now in between this, I will like to, I don't want it to have this regions, so I will just try to delete these regions in between. Okay, so like this, these are the regions which I don't want. So one more time I just click on body delete operation, make it apply and generate. So now you will see the arrangement which will be only with the fins. Okay, so this is how the arrangement which we can see now. It is with only the fins. But again, the task is not over. There are multiple things which is required to be done, and that we will follow first, and then accordingly we'll do. Okay, so the first step which we are likely to have, this is the object which has been sliced here. So I will make this as a uniform object first, and then I will proceed with the next step. So one by one you can do the boolean operation, because there are chances you may make error. So this is the first body which has been unite here. So now I will just carefully select this body, this one, this one, this one, this one, this one, this one, inside. So only select the inside one only. We are not interested in any other body which has been available here. Okay, so you don't have to select the internal one, we are just selecting the outer one right now. Okay, so just select on the both side here. Okay, now I will just try to do the boolean operation. Sometimes you may get error, as I said earlier, but like just like here you can see the boolean operation is not complete, so we may not be able to follow this. So what I will do, I will just do one thing. I will hide these bodies which are here, and first of all I will try to do boolean operations for this only. Okay, so whatever this boolean I have, so okay, so just delete it otherwise. So select these bodies which we are having here. So let's make it boolean, make it unite. Okay, now it has been successful. You can see here earlier it was not showing, so now it has been successful. So you can actually, now what I will do, I will just select this and this, and I will hide this body. Now I will just make sure that internal also been uniform up to this. So let's make this is to be boolean and unite. Okay, now the thing is, this is one body here, this is a zone, and this is a zone. Okay, so purposefully I kept it isolated because this is the zone which we are going to specify as a fluid. This will be space, and this one will be subjected to convection uh, over there because of the fins. Okay, so let's make it show all bodies here. Now what I will do, I will just select all these bodies here, and I will select this one. Let's create boolean operation. Just check we are successful with this boolean operation. We could have added this as well, but there are chances of error, so that's why not added. So better way, one more time do the boolean operation and complete the task. You can see now this operation has been completed. So we are left with only two things. This is the solid part, then we have the fluid which is present inside. This is the fluid which is present inside, this is the fluid which is present inside, and this is the fluid which is present inside. So we'll define this with respective names so that it will be easy for us to specify the things. So what I will specify this, I will specify this as a copper, or I will say pipe with fins. I will specify this as a pipe with fins. This zone will be subjected to air, this will be subjected to say working fluid. So I will say this is working fluid which is inside. This is your air, this is your air, and this is also your air zone. So this is the three air zones that we are going to have. You can make this as a unite part as well for this particular case, because this is the portion which is going to be filled with remained with air, or we can say the evacuated space, and remaining will be your working fluid. So you can actually make all this as unite as well. Okay, so this is one important task which we can do here. So let's click on boolean, make it apply, and this is now, this is, you will see pipe with fins, then this is a fluid. I will more specifically say there is a presence of air here, and the last one here is a working fluid. So carefully you have to check, working fluid is fluid, air is a fluid, and pipe with fins should be a solid one. Now if this is the task is done, now we can proceed for the next step. So if you are carefully understood, this is the section which relates to the pipes with fins. Here we have specified the air zone, and here is the working fluid. So let's save the work. Okay, so let's save the work. I will put a folder, let us say heat pipe with fin 1 mm. Okay, so I will give the same name here, copy address the text, heat pipe with fin n mm. Okay, the same name has been given. Let's make it save. So once this is saved, you can easily proceed for next step. Even if you are taking some break while preparing all such cases, you can go ahead and do the remaining task as well. Okay, the first phase of geometry preparation is over. Now you can just jump to the mesh part. Okay, so let's open the mesh part. So click on edit. So the next important step is defining the zones, because this is very important when we proceed for the meshing, as well as when you go to the setup. That's why it is very important. You should define the things, and it becomes slightly on the easier side if you are proceeded with that particular arrangement. So this is how the geometry which is visible to us as of now. So first of all, I will just generate a default mesh here. So later on we will like to have this as a comparatively on the finer size. Maybe I will just try to take it somewhere the nodes and element around 10 lakhs, so that I will not have to spend more time, especially on the iterations. So I take it 0. Say 0.005 here, and let's make it generate. So let's take it 0.005, and let's check out how the mesh is, especially on the fin surfaces. If that is good, we can actually go ahead for the next step. So this is doesn't looks to be on a better side, so I just put it 0.001. Let's make it generate. So definitely if you are trying different meshes, then the time requirement in this case will slightly go on the higher side. Okay, so this is again the mesh which is with 1,26,000. So not much of the variations as of now. So I just put it 0.0005, and let's make it generate. So we are just now around 1,23,000, sorry, 1 lakh somewhere. So I took it 0.0005. So this looks to be quite better, but again, for the zones which are especially toward the fins, we may want with some finer size of mesh. So this is one of the count which we can go ahead. This is 1,60,563, 4,83,385. So you can have some in between value as well. So let us say if I take it 0.35 and just see what happens. I just click on generate. So definitely if you take it 0.005, sorry, 0.005, the time requirement will be on the slightly on the lower side. But there are maybe chances of floating point exception error. So because especially the fluid zones are involved, and that's why we might be more interested in making it better, especially on the fluid zones. Okay, now 2,45,486, then 8,70,293. So this looks to be quite better for me. I can take it more finer as well, but I will preferably not, because there may be limitations with uh, the time requirement in other cases. So this is the first thing which we are done. Now, so now what we will do is we'll define the heater and evaporator sections. So let's specify this. So this is the place where we are going to apply the heat. So I will just put it evaporator, and let's take the other side here. So slightly zoom in. I want this to be complete. So I may just say select all. This is the one which I don't want. So air and okay, so I will just go back to here mesh and will select it one by one. I will, to avoid the errors. So make it properly visible. So this is what we are selected. This is also we are going to select here. Then all the pipes we have to select up to this. Okay, similarly on the back side we have to select. This is the similarly this region we want to select because I want to apply convection. So this was left. So now we have selected each and every region. So I will select name selection. I here put convection. I specifically mention this because I need to apply the convection coefficient later on, and that's why it will be easy for us if I am specifying here itself. Otherwise things will become slightly difficult to do so. So this is one case. Another thing that we are going to provide is the wherever the working fluid has been there, so that region we are also going to specify. So for this I will hide this body. Okay, now for this I will select all of the surfaces for this. Here I will select. So I will give this as fluid volume, also you can define. So I just specified this as a fluid volume, and now these are the three boundary conditions I have. Let's show all bodies. So you can see this is evaporator, and then this is convection, and lastly it is your fluid volume. So just make it update. You will see the option mesh translation to fluent successful. If this doesn't appear, then you have to refine the mesh size. So this, if this is doesn't appear, then you have to go with that particular process. So just go back to workbench window and click on save button. Once this, okay, so the next step is your setup. Just click on edit, go to the setup, select the double precision. I will just select the maximum number of cores which are possible with my computer. So let's take it 16 and then I will proceed with ahead. So let's now the few important things which we did earlier, so that will be helpful for us. Just like we have specified the convection, so we'll be applying the boundary condition there. We have specified the evaporator, so we are going to apply the boundary condition there. uh, so this is how the object should be visible. Just click on this styles, select the transient model, put it in gravity. I will just put it here is a minus 9.81. Then go to the material section, sorry, go to the model section. Multi-phase I will select here. So the number of phases which we are going to select, I go with volume of fluid and I will select here the 3 number of phases, and you click on implicit body force. I just make it apply. Okay, I have not defined any material as of now, so I am not going to go in the phases as of now. So once I define the material, then I will come back. So just go to the volume in energy equation, just turn it on, then make it viscous. I will put it K epsilon, then I will put it enhanced wall treatment, thermal effect and curvature correction, and let's make it okay. Okay, so next step is I just go to the materials. In materials we are going to use water liquid and as a material. So air will be there as it is. I will just water liquid and I will have the water vapor which is available. So let's copy in, then close. So these are the 3 different materials: water liquid, water vapor, air will be present, and then okay. So instead of aluminum, I need copper over there. So just go and select the solid as the copper. Make it copy and then close. Okay, now this is the done. Go back to the model one more time. Go to the multi-phase. Now select the phases. So the primary phase I will select as the steam which has been generated, or I will say the vapor. So this will be my primary phase. So I will select water vapor. Make it apply. Then secondary phase I will specify water liquid. So one more, first one I have specified. Now this will specify water. So specify accordingly water liquid. And third phase that we are the phase 3, that is again secondary phase. We'll specify this as a air. So accordingly we have to specify, and it should have been applied there. So carefully you have to just observe which is our primary phase, that is we have selected vapor, water vapor. Secondary phase we have selected water, that is water liquids. The secondary phase we have selected again air. So this is what we have done. Go to the phase interaction. You will see here. So I will just make it constant 0.0736, that is the surface tension I specified. Here also I will specify the surface tension 0.0736. Here also I will specify, because 0.0736. Surface tension force modeling, I will put it wall adhesion, so jump adhesion, and make it apply and then proceed for the next step. So heat mass transfer reactions, I will put it 1. I will select water here to vapor. I will specify evaporation condensation. So I will just put here as a 303 Kelvin for our reference. Make it apply. Make it apply and then go ahead. So once this is applied, you can proceed for the next step. So this is a very important task which we have done. So we are left with the models, we are done with the materials. So while doing the materials, adding the material itself doesn't mean you have defined the things. So we have to define this in cell zone conditions. So just go to the zone types. So wherever you are having air, you have to match it with the air. Okay, so this is here you are having air, so just match it with your air. Wherever we say, okay, so make it then working fluid. So working fluid will be your water liquid, so you have to match with this with the water. So this is very important step which we have to follow, because till the time we don't define where the water and other things are been present, it is of no use to specify the things. So here I need to select copper, sorry, make it copper, and just make it apply. So we are done with the cell zone conditions. So this is very important steps which is to be remembered. Now in operating condition, I will select the operating pressure as 4000 pascals, and let's make it okay. Now next is I go to the boundary condition. As I said earlier, convection, I will specify heat transfer coefficient. So I'll specify this value which is around 15 watt per meter square Kelvin. So this is again a copper arrangement is there, so make it apply and then close. Evaporator, this is again you have the material as a copper, so select copper. Now what was, so carefully select, so what was your heat flux, I will just put it here as a 20,000 value, 20,000 watt per meter square as a heat flux I am specifying. Let's make it apply and then close. So next is the fluid volume. Just go inside and just see. Here I have to change this contact angle 20. I just change this contact angle 20, and I just change this contact angle 20. So make it apply and then make it apply. So here also I will select the contact region. So you need to specify that value, this contact angle. So specifying this is equal to 20. This I will so specify this is equal to 20. This also I will specify that is equal to 20. Then make it apply and then close. So let's make it apply and then close. Okay, now next is just check all these walls wherever we have to apply uh, the contact angles. So wherever the options is available, accordingly I will just put it the contact angle here, so that is equal to 20. So at all the places I will just go and make it. So here wherever the options are available, there only we'll go it and make the changes for the contact angle. So make it 20. So here also we'll make it 20, and the last one also will make it 20. Let's make it apply and then close. So maybe on the shadow part it may not be visible. Okay, so here is also not there. So let's check it here. This is all the shadow part, which is, so this is pipe with fins. Okay, this is we already done. Wall 23, just check, already done. So wall pipe with fin, so this is the material which we already had. So change this is to copper, make it apply. Here also this zone, so specify this is to be equal to copper. This is also to be equal to copper. Wherever you are observing, make it apply. And I think it was here. So everywhere ensure that you have specified the contact angles, and then you can proceed for the next step. Okay, So now boundary conditions are done. So you can go to the report definition. So in report definition, surface report, you can say area weighted average. So if I want to know the total temperature of the system, in that case you can go with that. If I want to know the fluid temperature, so accordingly you can select that. If I want to know the temperature at evapor on the convection, so wherever the convections are taking place, say temperature at fins, if I want to know, I can just select the fins. You know the convection will be here, and you can just click on OK. So here, if you want to know the phases, say whatever the water volume fraction, if you want to know, or if you want to know whatever the liquid fraction of volume fraction of steam, you can select that particular option. And wherever the fluid region is there, so you can select the respective case. So we are not going to do that. So let's go with the next step. I go to the initialization. So just click on initialize. When you click on initialize, the patch option will be visible. So now here just carefully do water, I will say volume fraction, here it is 1. Where is the water? There is the working fluid. So just click on patch. Okay, so this is what we have to do. Then go to the calculation activities. I will say auto save option, that is 20. Then I go to the solution animation, say contours. I will select temperature. I select the total temperature of the system, and you can select all regions. Go to the color map, instead of exponential I select it float, make it apply, then close, click on save display. Now here the things will be visible. Okay, so instead of this wall total temperature, I will just select wall temperature rather than total temperature. Okay, so this is how it has been appeared. Then close this window, select the contour 2. If you want some different orientation, you can select the different orientation as well, like here uh, left, back, front, you can select. I just make it okay. Now I go with another animation. So contours, I select now phases. Here I select phases of water, water volume fraction, and where is the water present? In this region the water has been present. So just you have to check it uh, by generating it. So let's click on apply, make it save display. Just observe how it is visible. Okay, so you should see the volume fraction of water. So if this is properly visible, then you can select the region and accordingly you can go ahead. So this is how why we have defined this particular thing, fluid volume in a mesh. So this you can see now it is useful for us. So here I will select contour volume 2. I will select as a volume fraction. I will select water volume fraction. So this is your animation. So let's make it okay. You want the front view, you can accordingly select the front view as well. So the first animation which we had, so that was visible. Go to the run calculations. Instead of the fixed time steps, I will go with the adaptive time steps. So let us say for the first case, I will just run it for one time step, and I will select the time step size as 0.0005. I will not take it to the power minus 10 to the power minus 5. So I will take it 0005 and I will start doing the calculations. So I just run it for one number of time steps. So again, definitely this is the task which required some huge time. I will not say this simulation will be completed in next 1 or 2 hour. Probably it may take some days, maybe 2 days, 3 days, to generate the kind of pulsating flow, because it may need to have the time step size to be comparatively on the smaller size side. That just like we are taken 0.0005. If you take a very big time step side, there are chances of the floating point exception error, and that's why it is very important that when you run the simulation, you have to run it for smaller time step size here. Again, whatever the mesh size we have selected, so based upon that particular mesh size also, the time requirement will be more or less. We purposefully tried to take the mesh size comparatively on the lower side, that is below 10 lakh number of nodes and element. So definitely, if we are on the lower side, the time requirement will be less. But if we are taken very fine mesh, so definitely the time requirement will be more. Another thing is, this is just about the prediction which we are done, but in some situation you may get, because of there is no, maybe the case that whatever the fluid zone we are having, there may be not be having a proper mesh over there, so there are chances of floating point exception error. If such error occurs, then one thing which we can do is we can change the initial time step size. Just like we are taken 0.0005, we may make it 405 or maybe 505. So this is one we can do. But if still we are get, and we can run the iteration just like the way we are running, but if the same problem it appears again, then definitely we have to go back to the mesh and we have to change the element size. So this is one task which we have to do if the floating point exception errors occurs. Again, predicting this error to occur is very difficult. There may chances you may run the iteration for 1 lakh and the error may occur in between, or sometime it may also not happen. So that's why it is very important to select the proper mesh size which we are having, and whatever the initial time step size you are selecting. So this is also very important task. Okay, so this is how, let's see what here. So right now we don't observe much variations in the temperature here. uh, Sorry, I think we selected the pressure graph. Okay, so we'll just modify it once this is completed. So this is what you can observe: the temperature gradually increasing at the evaporator section. I think while selecting the this one we might have made some mistake, so it is showing the value of pressure. So we might have to just go back and check it, this value. So this is again, as I said earlier, we have to run it for long time, then only we'll be in better position to predict the things. So you can see the calculation complete message has appeared. So we'll just go back and check what was the error here. So go to the edit. Yeah, you can see here we have by mistake selected temperature. I will select the here as a temperature, or you may say as a wall temperature here, and convection. So let's make it okay. Okay, so let's, or we will generate one more, or let's see what if I just click on calculate, whether it appears or not. If it does appear, then there is no issue. Otherwise, we'll generate it one more time. So let's make it overwrite. Or if this doesn't appear, you have to go with initialization again, and you have to proceed with the same task. So you have to so this is here it is not appeared, so you better way generate one more report definition and accordingly try to do this. Or the another way is you just go ahead to click on initialize and do the process again. So this is one way of proceeding with this. So we'll just one more time. While doing this, you have to carefully take a look at the residual, how it is moving. So whenever we are observing the floating point exception error, there are chances these are been intersecting with respect to each other. So the lower one and the upper one, and you can predict when the floating point exception error can occur. So this is one way of predicting the things. So we did it slightly on the wronger side, so you can modify it, and this is here. You can see the temperature distribution here. So we have, you can see it is 1.1294 e to the power 02 minus 02. So right now the time flow time is 0.01. So you can just understand the variations. So with 0.01 second, it's very we might not be able to see much of the variations which are here, but once this is completed to around, like say 1 second, 2 second, maybe around 10 second, it will be quite easy to predict the things for the given case. And that's why the time requirement is slightly on the higher side. We may take the initial time step size maybe at 0.005, but there are chances of floating point exception error in that particular situation. So as we have told that the floating point exception error when can occur, it is slightly difficult to predict. So if sometime you go with a proper mesh size and you take 0.005 as well, and you might not get the floating point exception error for particular flow time. But if it occurs maybe at the later stages, it may be slightly difficult situation. So let's see here. You can see how the temperature is varying for evaporator, the red zone. Actually, we can plot two more curves as well. One of the curve will show the evaporator temperature, other will show the convection where it has been applicable. So that curves we can generate. I will just show you how it can be there. So let's make it okay. Let's click on save. Just go back, go to the report definition. So I select surface report, area weighted average. So instead of pressure, I will select temperature. I will select the wall temperature here. So I will select the convection. So here specify convection. Okay, so for convection I am specifying this is one case. Make it okay. one more, as I said, area weighted average, temperature. I will select wall temperature here. I will put it evaporator. So I will just name this as evaporator. Just make it okay. So likewise, the things can be there. I just click on calculate, and let's see how it goes. Okay, just put it to 1 only. So just checking how, whether it appears or not. If it doesn't appear, then I will just go on initialize the things. Okay, so you can see now the two additional curves will be available for us. One. Okay, so here you just see this is the wrong one which we did. This is contours of volume fraction water. This is contours of wall temperature. Then the one just now we added. So right now we don't have any value which is available here. Okay, so let's run the simulation further. I just put it the value around 10, make it calculate, and let's click on OK. So as I said earlier, it will take some long time to visualize the pulsating action. It will take some long time to visualize the pulsating action here, as well as the temperature which is rising on the other end. So this is the task that maybe take some long time. So by that time, I just close the meshing part, which is not required for us as of now. The geometry part also, which is not required for us as of now. So this will go on to close. So the thing is, when you want to run the simulation, like as I said earlier, this simulation has to be run for some longer time. You can interrupt the solution by clicking once the calculations are complete, and then you can go back to the workbench window, save the work, and then you can close the Fluent window. So this is one task which can be done, and you can resume your work by opening the file again. Even if you shut down the computer, you can start from the last step where you are ended. So this is the way by which the simulation can be run. So as I said earlier, it may take some long time to observe the pulsating action, as we have taken this very small time step size. So just will wait for the simulation to takes place, and accordingly we'll update. So we have completed almost around 20 to 30 you can see that is 32 time step we have completed. So I will just try to show you what we did. So this is the contours of volume fraction we are available. So this is the temperature which we are having, the convection temperature which we have specified for the convection zone. So that is here. Evaporator temperature, you can see it is gradually increasing. Okay, so this is what we have set earlier. So this is how it can be done. um, so this is contours of volume fraction. If you want it for steam, you can do it for the steam as well. So likewise, we can say the various curves which we can get. So I just click on save the button, and I will try to run the simulation again. So we'll put some higher value now. So we did it for around 32, I guess 32 time steps, which you can see here. So I just put it now around 68, so that we'll reach to around 100. Let's check whether the work is saved, and let's click on calculate. So you can just check out the task manager, how the usage has been there. So the CPU usage, how it is there, at the same time how what is the memory usage which has been available. So this is also one of the way by which you can track how the computer is performing. Sometime if you are running it for some very long time, as I said earlier, you can stop the process and you can shut down the computer and you can run it again. So if sometimes you observe that you are observing so much dips which are coming in this particular we can say activity. So it means you have to restart your computer, and that's why when you run it for some long time, that time you have to do this. But right now it is quite performing well, so there is no such issue as of now. So I am not observing, especially on the fin side, much variations in the temperature, which is quite here near same. Here we observe the rise in the temperature. So we have to wait again. We haven't seen any kind of say fraction which has been generated, that is steam has been generated. So this is not which we are observing right now, but definitely after some time it will be visible to us after performing some iterations. So we'll keep this running, and we'll just check it out how the results are there after around say 100. So we are still running the simulation. You can see the scale residual here. Then so this is the contours of volume fraction. We can see the development is not there as of now. So you'll see the contours of wall temperature. Then this is the convection temperature at the convection region, the temperature at the evaporator region. So this is we are around 0.45 seconds. That is your the flow time right now. So we still need to run the simulation for a long time in order to visualize the uh, pulsating action. So this is not visible as of now. So we have to run this for a long time. So we are around mm, so this is how we are here. So you can see the flow time nearly we are approaching to 1 second. You can see this alternate liquid and vapor slux are been visible now. This is just at the initial phase of development. We have to run this further. So you can see now this temperature curve slightly getting up. So again, not much of the variations in terms of the temperature for your the region where it's related to the convection. Here we can see the evaporator temperature is continuously rising. We haven't seen a kind of flat curve as of now. So there may be the case where the curve will likely to get flat. So this is your scale residual. So the number of iterations are continuously going on. So you can see 32945. So these are the number of iterations as of now. So the flow time is also, as I said earlier, it is we are reaching to around 1 second. So the simulation is performed for around 1901 time step. So the current flow time is 1 second. So as you can see here, so this will represent the contours of wall temperature. You can see the temperature which is reached around 308.14. Then you can see the contours of volume fraction liquid, that is water. So you can see the pulsating action just has been started, but it will again definitely will take some time. So this is the temperature at the region where the convection is taking place. So this is another one, that the temperature at the evaporator. So this is what we can visualize from this. So we have to run this further in order to visualize the simulation with the pulsating action which is taking place from one end to other end. So running will further require more number of iterations. So right now we are around 38,020. So it has to be run further in order to visualize more properly the alternate liquid and vapor. So we are run the simulation for around 1.3369 seconds. We have around 51,060 iterations and 2563 around the time step value. So what we can visualize out of here is the alternate liquid and vapor slux are in form. You can see here. So the contours of wall temperature which you can see. Then this is the liquid fraction which we are having currently. Then evaporator temperature. Then the region where the convection has been taking place. So right now we are not seeing any rise in the temperature. So this is your scale residual. So we need to still run the simulation for some long time. So we are running it from last 2-3 days. So till the time we don't observe the complete liquid and vapor slug, we have to visualize this. So this is how the alternate liquid and vapor slugs are invisible as of now. So you can see the side view of this. So this is the front view here, and this is your isometric view of the object. So alternate liquid vapor slugs are invisible here. So the fluid will be having tendency to go up. At the same time, we have provided the convection at the top. So that may result in the condensation that is going to take place. So till the time these particles are not reaching up to the top section, will be not able to visualize the condensation which is going to take place. So we will have to run this simulation for some long time again. So total 51,000, as I said earlier, the iterations have been performed. So time step size we have taken, as I said, 0.0005. This is comparatively on the slower side. So again you can see some small development which have been taking place. So this will definitely push the fluid in the this top section where the fins have been provided, and we'll see subsequently we'll see some rise in the temperature as well on the subject on the portion which are been available here. So once the curve is likely to get flat, you may see that temperature may not change further, but as of now this point hasn't been reached. So still we are having the curve which is on the rising mode. There is no such change as far as the convections, the where the convection is likely to take place. So temperature is again around 300, so not much of the change as of now here. So we are around 1.48 seconds. You can see time steps that have been completed are 2950. So with this 2950, you can see the alternate liquid and vapor slugs are been formed here. So this will show you the contours of wall temperature. We reach around 310. Then you can see the curve evaporative temperature, it is rising over here. We haven't seen much of the changes as for the previous scale. This is the scale residual which we are observing. So we have to run this further in order to completely visualize the alternate liquid and vapor slugs. So here you can see we have set the volume fraction for water. So we have set this from volume rendering first when we are defined. Then you can see water volume fraction. We have selected range as a local. Resolution we have taken as a 100, and on the scale we are just observing the volume fraction liquid from say 0 to 1. One more volume rendering I will add. So this is for my temperature. So I will select here temperature. So instead of the global I will select it local, and here I will put the resolution to be around 100, and let's make it apply. So now you will see the temperature scale as well. So earlier we are able to see the volume fraction that is for your liquid. Now we will be able to see the volume fraction for the wall temperature for the given case. So depending on the what resolution you have selected, the time required will be more or less. So right now we have selected around 100 resolutions. Okay, so you can see here the temperature is been visible. I will just hide the first one. So this is the second. This is temp for your temperature. If I just go here, and you can see this one. So likewise things are been visible to us. So we have performed the simulation for around 1.65 seconds. You can see 66,609. So these are the iterations which have been performed as of now. You can see the alternate liquid and vapor slugs. They are clearly visible in the evaporator section. Now this will go up and it will move towards the condenser section. So 3,331. These are the time steps which have been completed as of now. As you can see again, so alternate liquid vapor slugs are already formed. So this will push the fluid and it will move through this particular region where the fins are been provided, and then there it will follow a kind of loop path. So that pulsating action will be visible when we run the simulation for further some time. So this is the contours of wall temperature as of now you can see. So this is the fins region we are having. So this is the fluid zone which we are observing right now. This is the convection. So we have some slight increase in the value. Again, it is very low value, but some steps are being observed where the temperature is likely to get increase. So this is the evaporator temperature which is increasing continuously. So this is the scale residual. So we are running it further. So we need to run this further in order to visualize the complete pulsating action which is going to take place throughout this heat pipe. So we have performed the simulation for around the flow time of 2 seconds. You can see the contours of wall temperature right now. So this is the contours of volume fraction. So you can see the alternate liquid and vapor slugs are clearly visible. Now the fluid has moving upward, and after some time there will be the pulsating action that's going to take place. So we have to run this further. We are at up to 4248 time steps. So we might have to run this further in order to visualize completely the pulsating action that is going to take place in this particular pipe. If you see the evaporator temperature is continuously increasing, then this is we say slight increase in values. Again, not much significant, but till the time this temperature will rise up to the section where the convection is likely to take place, you will see some rise, and definitely it will require some more time for the case. So this is a scale residual which you can visualize. So we have performed the simulation for around 2.4 seconds. So you can see more than 1 lakh iterations have been performed. The time step value is 5290, just now we have seen here. So this is the contours of liquid fraction which is available. You can see the alternate liquid and vapor slugs are been visible. So this has been pushing the fluid in the upward direction. So these are the alternate liquid and vapor slugs. So if you see the contours of wall temperature, so you can see here, then this is the temperature rise which is taking place at the place where the convection is taking place. So very minor variation as of now over here. So then this is the evaporator temperature, a curve which is representing the maximum temperature right now around 315.3991. So this is your scale residual. So we need to run this simulation for some long time in order to completely visualize the alternate liquid and vapor slugs which are moving towards the convection region. So with the current flow time, the simulation is run for around 3.22 seconds. You can see the liquid, alternate liquid vapor slugs, they are moving upward. Right now, where the pulsating action will take place from left to right or right to left, this is not clear. Once we are running it for further, then it will be clear. So this will show you the contours of temperature, wall temperature. So this is where the temperature is slightly increasing in the convection region. and this is your the vapor temperature curve. So we have to run it further in order to visualize the alternate liquid and vapor slugs. They may be moving either left to right or maybe from right to left. So at the present time, we are in the simulation for around 2,15,657 iterations. You can see 10783 as a time steps. So this is the wall temperature. Here you can see the alternate liquid and vapor slugs are being formed. So one of the tendency which we are observing is it is coming down over here. So the convection temperature, the convection region where the temperature is. So this is rising. One important thing which we have observed is the curve has become slightly flat on this particular region. At the same time, slightly, if you see the temperature here, that is 325.96, and here if you see the temperature, so slightly decrease we have seen. So that is because of the alternate liquid and vapor slugs which are coming back to the evaporator section. So we will run this further and they will check how the temperature varies with respect to time. So right now total the time which has been occur is 4.5 seconds. So for this the simulation is running. So this will show you the scale residual. So there is a drop in temperature which we can see here. So this point represents 325.97 and this point represents 324.70. So this has happened because the alternate liquid and vapor slugs, when they are moving, while from this region the liquid is coming back to the evaporator section, and that results in lowering the temperature. So this is observed, can be observed with the help of the curve which has been here. So that shows the lower temperature at the evaporator. At the current state, the simulation is being performed for 14,000 seconds. You can see the wall temperature, then you can see the contours of liquefaction which is available here. Then this is the curve which is moving up and down. So the evaporator temperature has reached to topmost value. Then because of the liquid and vapor slug, this temperature has dropped. And then again you will see some increase in the temperature here. So this is the temperature which is near to where the convection is taking place. This is the last one, is the scale residual. So now we'll just go to the post processor, and here you can visualize the contours of temperature. Then you can visualize the contours of liquid as well. So individually this is temperature. If I just add this, you can see the liquid as well. So alternate liquid and vapor slugs are been visible here. Now we'll run the simulation. We'll run the rendering now to visualize. You can actually change the resolution as well. So let's make it to around 200. So we have changed the resolution. First one is also 200, second one is also 200. So this is only liquid of slugs which are. So you can select time step animation. You can click on save movie option. So depending on where the folder you want to save. So right now let's prepare one more folder. or you will use some other destination. I put post processor image, liquid fraction, click on save, go to the option, here you will select custom, then I will select this too. Go to the advanced, say select higher, select the directory as well. So now I will go with choose, then click on OK. Now we have to start it from 0. So this may take some time. Okay, so this is the initial stage we are having. If you just want to add this, you can add this as well. Okay. So now click on so this process now started for rendering. So liquid will move up. So one by one image files will be prepared. So likewise one by one the images will be prepared. So that there will be total around 1000 images, and you will see the alternate liquid and vapor slugs which have been formed. So you can see the second frame now. So this will process the will continue. Not only 1000 process, as I said, uh, whatever the last time step you are having, so accordingly things will proceed. This graph represents the evaporative temperature with respect to flow time. You can see the graph is rising, where the temperature rises to around slightly above 325, then it drops and again it starts rising. So this happens because of the alternate liquid and vapor slugs which are coming towards the evaporator section.